Okay, so welcome back, guys. So it's time to start. Today we will really have an exciting lecture because we are starting a completely new set of topics. So what we did in the last couple of lectures is that we talked about the crystalline state, the state of the material where we do have the long-range translational order. We learn about symmetries in these materials, and then we also learn how these symmetries influence the properties of the materials. So this is what we concluded last time. And what we will do today is that I will introduce you a completely new set of materials that are neither amorphous, the class of materials that we covered in the first part of the course, neither crystalline materials. So specifically, we will talk about liquid crystalline materials, plastic crystals, etc. So I will just introduce you the basic concepts. What does it mean that the material is liquid crystalline? And then next time when we meet, when you return from a relatively long break, we will talk about the applications of these materials. So I would like to start this lecture with a story. Okay? And the story happens in 1981. So you should really follow what I'm telling you because there are three incorrect things in this story. Okay? At the end, I will ask you what are these three things. Okay. So it's in 1981. So this is me. So, and I'm playing with my teddy bear. Okay. So you can guess my age, right? So, and one day, my mother comes. Okay, so this is my mother. She has a short hair. That's true. That's true. That's the true part of the story. And so she's very excited. Okay, she's raising her hands, and she's really, really excited. And she tells me the following thing. I read on the internet that they discovered a material, a crystalline material, with 5-fold rotational symmetry. Okay? So that's the story. Okay? You have everything that you need to know. There are three things that are incorrect here. Okay, so I'm asking you, what are the three things that are incorrect here? Sorry? Sorry? Oh, okay. So the story happens in 1981. So I'm playing, and my mother comes into the room, and she says, I read on the internet that they discovered a material with a 5-fold rotational symmetry. Yes. 5-fold rotational symmetry, that's right. So you're saying that this is incorrect? Okay, good point. Anything else? Yes. There was no internet at the time, can you imagine? So there was no internet. Actually, okay, there was internet, but we were not using it. Okay.
Well, wait, I think maybe it's true. Maybe like the 5-fold is like crystals. You said we're not going over to crystals, right?
So can you say it again?
Like, I don't know. Was the phrase you say like crystalline material 5-fold? Because that was wrong.
Okay, would that be, if I just said crystalline material, would that be different from just a material with 5-fold rotational symmetry? Would that be in any way?
Have to have translational, and that's what limits the rotation.
That's right. So this is what we learned so far, right? But are there any materials that do have 5-fold rotational symmetry that you know of?
Not that I know.
Probably? Well, this is actually what we will learn today, is there are classes of materials that do have rotational symmetries that are not necessarily allowed in crystalline materials as we defined them so far. Okay? So these are so-called quasi-crystalline materials. So everything that we learned so far, you know, in general is correct, but we will see that the definition of the crystalline material dramatically changed. And actually, the third point that was incorrect in this story is that this happened in 1982. So the discovery of quasi-crystals happened in 1982. So there's just, but I don't blame you. You don't necessarily need to know the years. But so this particular year was very exciting. You know, my mother would be very excited if she knew something about quasi-crystals at the time. But what happened that year is that this type of diffraction patterns have been, you know, attempted to be published. It's a correct word, but they were discovered. Okay? So this is a diffraction pattern from a particular material that has this particular composition. So it's an alloy between aluminum, copper, and iron. And if you look very closely at this electron diffraction pattern, you will see that it has a 10-fold rotational symmetry. In other words, if I count the number of the spots, I would have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And everything that we learned so far, we learned that this is impossible. If you have a crystalline material, and if that particular material has a rotational symmetry, and if there is a rotational symmetry, this would be impossible. Okay? And as it turns out, there are materials that have these very discrete diffraction patterns that do have the symmetries that by traditional crystallography should not exist. Okay, so what really happened in 1982 is that particular material was discovered, or it was investigated in depth, and it happened to be aluminum manganese alloy. And again, it showed this very discrete set of points. We will see that this was the very first material that was discovered with this property, but actually there is an entire class of materials that can be synthetically made, that can exist in nature, that can even come from space. So the previous example that I showed you was the material that came from a meteorite. Okay? And again, what they show is that they can actually have the symmetries that by traditional crystallography are forbidden. For example, they can have 8-fold rotational, 10-fold rotational symmetry, etc. And when you even look at the surface of these materials, you will see that their shape resembles 5-fold rotational symmetry. So these are two images. Scanning electron microscopy is just an optical image of two crystalline materials that are quasi-crystalline. And for example, if you even look at the shape, you will see that they have these five shapes or five facets that somehow resemble the internal symmetry of the crystal. Yes, did you have a question?
So because these don't obey the rules of translational crystallography, they're called quasi-crystals, not crystals.
So we will come to the exact definition, but so we will see that they do not have translational order. They do have a long-range rotational order without preserving the translational order, but we will come to that. We will see that the definition of the quasi-crystal, and as a consequence, the definition of the crystal itself changed with this discovery. Okay? So this is yet another example of a quasi-crystal, and when you look at, again, the surface of this material, you will see 5-fold rotational symmetry. And I told you that, well, the surfaces and the facets typically resemble, or they are indication of the internal symmetry of the crystal itself. Okay? So, and this would be just, again, yet another example of a material. This is the same material that I showed you the diffraction pattern of. So this would be now electron microscopy image. So when you actually look at the material in the real space, you are not taking a diffraction pattern, which is reciprocal space. This is what you would see, right? So you will see these individual domains that have this 10-fold rotational symmetry. So the atoms are arranged such that they have this 10-fold rotational symmetry. But when you look more closely, there is no translational order. Okay? So, and again, this particular example is from a quasi-crystal that came from space. So, this would be a calculated electronic surface of the material that has this type of a structure. So the question is, how come that they can exist? What kind of symmetries do they have? And how do we even define them? So traditionally, we talked about amorphous materials and crystalline materials. So now suddenly we have this new class of materials that is very, very new. So I would also like to give you a follow-up story. So the scientist who actually discovered these quasi-crystals, his name is Daniel Shechtman, and he comes from Israel. And he had difficult time to publish his results. So he was the first one who showed these diffraction patterns. And people simply did not believe him, because everybody thought crystalline materials have to have a certain set of rotational symmetries, and the diffraction pattern that he demonstrated or recorded must be an artifact. For example, if you have a material that is polycrystalline, perhaps the diffraction pattern actually reflects the diffraction from two grains that have certain misorientation. And it took him 2 years to publish his results. So he was really fighting against this established knowledge that we actually built in 312. I was convincing you throughout the time that the 5-fold or 10-fold rotational symmetry doesn't exist. And yet, he has to fight against that, right? And this is yet another example of how a Nobel Prize was given for diffraction experiments. Just to encourage you, if you know your diffraction, still time for Nobel Prize. Because again, if you know what you're recording, right? So if you know what the diffraction pattern represents, you can, in principle, reconstruct how your material looks like. So you have to be confident in your knowledge about what you're actually doing to be confident in your implications of your work. So he was really confident that whatever he's recording is from a material that is not necessarily polycrystalline, it's uniform, and yet he's observing this type of behavior. And I would just like to point out that his tie, he's really dedicated. So he even has a tie with a quasi-crystal structure. Okay, so as it turns out, the concept of the quasi-crystallinity is not new to material science. It actually existed in math for a long time, or relatively long time. But these are so-called Penrose styling structures. So Sir Roger Penrose was a mathematician, and in the 1970s, he developed this mathematical concept of the quasi-crystals. And the idea is that you do now have the ability to tile a two-dimensional or three-dimensional space using tiles, two different types of tiles in this particular case. So you do tile the entire two-dimensional space where you have rotational symmetry, but there is no translational symmetry. And just to show you what that actually means, so if you look at, for example, this particular object, or what we traditionally in 301.2 call motif, you will see that it does show up throughout the space, right? And when you look more closely, you will see that the fivefold rotational symmetry is preserved long range. So when you look at the outside of the material, you will observe that the different length scales, there is fivefold rotational symmetry. And yet, there is no translational symmetry. So in other words, I can define these individual motifs, I can find them throughout the space, but they do not have translational symmetry. I cannot define two basis vectors or unit cell for that matter. Okay? So again, this concept existed in math, and then it was then applied to material science to explain the structure of the quasi-crystalline materials. And again, the structure of the quasi-crystalline materials is not necessarily easy to explain, but just in very simple terms, if you, for example, have two lattices, so this is just an example of a one-dimensional crystal, okay, or a quasi-crystal. So that is a combination between two one-dimensional crystals. So in the first case, you have a crystal that has the basis vector t, and in the second example, you have t prime, and their ratio is irrational fraction. In other words, in the first case, the length of this t vector is 1, and in the second case is square root of 3 over 2. Okay? So if you merge these two crystals, in this particular case, they are crystals because they have long-range translational order. If you put them together, so what I will have in C is simply A plus B. And I will end up in a situation where there is so-called self-similarity. In other words, I can look at this particular feature, and it will be self-similar to the feature next to it. And if I go further away, this feature will be self-similar to this one, etc. So there is this self-similarity, but there is no long-range translational order. So if you have two lattices, or if you combine two traditional lattices, and the notion is that the ratio between their basis vectors is irrational fraction, you will end up with a quasi-crystalline structure. So after this very initial discovery, there was a lot, there were so many materials that have been discovered to have quasi-crystalline structure that it really became an entire field in material science. They're very unique. Usually they are alloys, typically. But they also, for example, have higher electrical and thermal resistivity, and yet they're harder from their counterparts that have a crystalline structure. So if you take a quasi-crystal and a crystalline material with the same stoichiometry, typically quasi-crystals will be more resistant to electron and phonon law. Okay? And they will typically have different mechanical properties. So there are many applications of these materials, but again, they were also discovered, as I mentioned, coming from space. So this was one discovery in 2012. So this particular material was discovered in mountains of Russia, and then it turned out to be quasi-crystalline. And again, they can also appear in nature. Okay? So they're not unique to synthetic materials. They do exist, and They are, again, a new class of materials. So, because now there was this new discovery, there was an entire redefinition of what a crystalline material means. Okay? So what we learned so far, what we typically traditional crystallography tells you, is that the crystalline material is the material that has the long-range translational order. The new definition, so right now if you go to International Table of Crystallography, that definition will be different than in 1981. Okay? And the definition simply tells you that a crystal means, or it's any solid that has a discrete diffraction diagram. Okay? So if you have a material, if you obtain a diffraction pattern, whether it's an X-ray, electron pattern, if it has a set of discrete spots, by the definition, right now, it would be called crystal. And everything that we learned so far, all of the traditional crystalline materials would be called periodic crystals, and the quasi-crystals would be called aperiodic. So what that means is that now the crystalline materials are defined by the diffraction and not by the real space. What that means is that the crystalline materials, by the new definition, are defined by their reciprocal space. So you can ask a question, why did we learn about the reciprocal space, and why did we even learn about diffraction? And one of the answers is that right now you define crystalline materials according to the diffraction. Okay? So again, knowing both the real and the reciprocal space notification is extremely important. So just remember that everything what we talked about the crystalline materials, they would be periodic crystalline materials according to the new definition.